In a previous video, we defined the spectrum of a discrete time signal using the discrete time Fourier transform formula. We can use that. It is the theoretical spectrum, and that's the one that has all the nice properties. However, if you actually wanted to compute it for data from a signal that was a measurement, there's a problem, and we're going to talk about what those problems are. Well, in order to be able to compute a spectrum, to do what's called spectral analysis, we're going to have to define something called the DFT. This isn't a new transform. It's very closely related to the DTFT, but if you switch to using the DTFT in practice, you'll now be able to compute the spectrum of any signal that you have. We'll, of course, explore its properties, and one of its properties is particularly interesting and very, very useful in applications. Well, what are the problems with the discrete time Fourier transform? So here it is. We've seen this formula before. And what are the issues with it? And there are two problems. One is the formula is geared toward infinite duration signals. This sum goes from minus infinity to infinity, and that, of course, causes troubles if you have data. How are you going to evaluate this thing? You have to store a lot of signal to do it. Well, I think the solution to that is pretty obvious, and that one is an easy one to solve. But there's one that's a bit more subtle and a bit more interesting, and that is that f is a continuous variable. F, of course, as we know, is in the range 0 to 1, and we would have to calculate this spectral formula for every possible value of f in that interval. And the question is, why do you have to compute them for all of them? And the reason is the inverse transform. So we all know that the inverse transform is an interval. And it's the fact that it's an integral is the problem, because I need to evaluate this integral, and that means I need to know that spectrum at every possible value of f. And there are an uncountably infinite number of values of f in that interval. So that makes it difficult to evaluate the original spectrum at all those points. And you might say, well, let's just approximate this integral. What do we care? I want an exact relationship between a spectrum and its original signal. I want to be able to get back that original signal with no error at all. And so the fact that we have a continuous frequency variable is indeed a problem. Can't really compute this formula for real actual signals. So how do we solve these problems? Well, I think solving the first one is pretty obvious. What we're going to do is restrict ourselves to finite duration signals, signals that are defined over 0 to n minus 1. So capital N is the duration of this signal, the number of signal values we have, and it's because we started at 0 that this upper limit goes to n minus 1. So that's pretty straightforward. That just changes these limits to be 0 to n minus 1. And so that's easy to fix. The solution, though, to f being a continuous variable is kind of surprising. We're going to sample in frequency. So we're defining a sampling rate, which is 1 over k, and we're going to evaluate frequency at little k over k for k, little k ranging over 0 to capital K minus 1. So why would this work? Well, let's think about the sampling theorem that we've already talked about. If we had an analog signal and we sample it every t sub s seconds, we know we can do that if the spectrum was band limited. And of course, the sampling rate was properly related to the bandwidth of the signal. So we sample in one domain, the time domain, and in order for that to work, we had to have in the other domain, the frequency domain, that it was band limited. Here, we're sampling in frequency. That means we need in the other domain that it be time limited. Well, that's exactly what we have when we made it finite duration. So we can sample this spectrum for when the signal is finite duration with no error if we make the sampling rate fast enough. We want k to be big enough so that we can get back the original signal from the sampled spectrum. So the question is, how big does k have to be? Well, I'm not going to appeal to the sampling theorem. That turns out to be the long way around. What I'm going to do is appeal to the inverse transform. So from all we know that the inverse transform formula, if it exists, has to be of the following form. We're going to sum the spectrum, the DFT, multiply it by a positive exponential, sum it up, and that should be at least proportional to the original signal. Now, what we need to do is just take this, substitute it in there for S of k, and see what it takes for the result of that substitution to be our original signal. This is a little detailed. It's gone over in the notes. You'll find the derivation there. And the result is very simple. For this formula to work, all we need is that capital K be at least as big as capital N, but it could be bigger. And as we're going to see in a second, being bigger is a very important thing. Now, I should point out that I have referred up here to capital K as being the transform length. And so because of this condition, I can change this up here to be capital K. And why that works is because suppose I have some signal here up to n minus 1, and what are the signal values up at k minus 1? Well, what I'm going to do is just extend the signal with some zeros. And that way I can refer to the capital K as a transform length. This is the actual length of the transform. And because of this property, it doesn't hurt to extend it with these zeros. Well, these zeros have a very special name, and doing this is called padding. So it's just jargon for frequently used in practice. So we're going to evaluate the DFT of a signal with a length that's greater than or equal to the signal's duration by just extending it with zeros, what we call padding. And we will be able to get back the original signal without any problem. There'll be no error in that at all. So let's see how it all works out. So we need to talk about the DFT and the inverse DFT. And here are the formulas for them. So the DFT is just as I've described. We're sampling in frequency at little k over capital K. And when you do have the requirement that capital K is greater than or equal to n minus 1, the inverse transform formula works, and that constant of proportionality that I mentioned before is the transform length, 1 over k. Now it turns out most software packages already take care of this normalization. It's built in, so you don't have to worry about it. If there's a function in MATLAB or Octave that says DFT of little s, then you take the inverse DFT, IDFT of capital S. This 1 over k is going to be taken into account, and you won't have to worry about it at all. With these formulas, we have a transform pair. So the DFT can be used for any signal that you want. You don't need a formula. All you need to do is to find the values of the signal, whether it be a measurement, whether it be a formula, and write a program that does this, and you'll wind up with the DFT. And computing the inverse DFT is about roughly the same amount of computational work. We'll get to the amount of work you need to do in a second. Let's see how this works for an example. So I want to be clear about the padding because this is an important concept. So here's a constant signal. So capital N here is 5, and the signal is just equal to 1 for all 5 samples. I've extended it with 2 zeros, so making the transform length now 7. And I now take this signal and put it into this formula. I'm going to change that to a capital K like I did before, and that I will get back a spectrum. If I take the results of that computation and put it into that formula, I will get back the original signal exactly. Now I should point out a technical point about this inverse DFT. Note that I have evaluated it only over the range 0 to n minus 1. Well, what happens if I evaluate it outside that range? Because of the properties of the complex exponential, the inverse DFT formula produces a periodic signal. This thing, this complex exponential, is periodic with period capital K. So what happens is you start evaluating it at n negative or n bigger than capital N minus 1, what you get are periodic repeats of the original signal. Well, if you go back to the sampling idea, this should be pretty clear. When we sampled in time, when we sampled a band-limited signal, once you sample it, the spectrum repeats in a certain way. Well, here we're sampling in frequency, and what has happened? We now get periodic repeats in time. And so this makes perfect sense because of the way we did the sampling to make things work out. There's no aliasing, if you will, because we chose capital K to be bigger than capital N. Well, since we restrict it to this range, what that essentially is doing is just ignoring all these periodic repeats. We don't need them. It's just the same signal values. Why take them into account? And we even can ignore the padding. We know what we padded it with. We know what the original transform length was, so we just can ignore those, and we get back our original signal with no problem at all. Let me go through an extended example here to show you how this works out in practice. So here's our constant signal again. And I've chosen it to be finite duration, of course. It's just going to be equal to the signal value 1. And the first thing I want to do is compute its DTFT. Well, that means I need to just put that signal into this formula. I now have finite limits corresponding to the duration of the signal, and there's the complex exponential I multiply it by. Well, how do I figure out this sum analytically? And this turns out just to be a special case of the finite geometric series. It's really easy to see, and I don't know if you know, but this is the closed form expression for the geometric series, and what we have here is alpha is e to the minus j 2 pi f. So all we need to do to find the DTFT is plug it in. So we get 1 minus e to the minus j 2 pi f capital N divided by 1 minus e to the minus j 2 pi f. Well, using the same mathematical trick that we used before, I'm going to pull out half the phase from the numerator and the denominator, and we'll get a very nice closed form expression. So we get e to the minus j pi fn times e to the plus j pi fn minus e to the minus j pi fn. And that's all divided by doing the same thing downstairs. F minus e to the minus j pi f. Well, you can easily see from Euler's formula that these are sine expressions, and so when you simplify everything, this is what you wind up with. So we get an answer which should look fairly familiar with what we've done in the analog world. We have a linear phase, which is to be expected, and then it turns out, because of the way the math worked out, we get a sine over sine, and this is called the digital sinc, and we define the digital sinc to be sine nx over sine x. When we were doing analog things, we had the sinc function, and what that equaled was sine x over x. And so you can see these are very close related. They're going to look very similar, with the difference that because this dTFT must be periodic in f, that's why basically why the sine is in the denominator. It makes everything periodic and over the right period. So everything's fine. So anyway, this is our dTFT of our constant signal. Now, here is the same signal, and we're going to compute its DFT now. Well, as we know, it's just going to be a sampled version of it, and you can see from the formula that it again is a geometric series, finite geometric series. So you can compute it either way, and we get the same kind of answer, and it's pretty straightforward to see that that's the case. All right, now what happens when we plot the answer? Okay, so here is a specific case. The duration of our constant signal is equal to 1 for 10 values, for 10 samples. And this is just a plot of the digital sinc function, and you can see it has all the kind of things you would expect. Peak at the origin, and it dies down. The difference here, of course, is that it's periodic, so this is going to repeat. This is negative frequency. So this is positive frequency, and that's the only thing I need to plot. Because of the conjugate symmetry property, I know that the negative frequency part is a mirror image of the positive frequency part, and because it's got to be periodic, this is negative frequency too, and it's also a mirror image about the point f equals 1/2. So that's pretty straightforward. Well, what about this phase? Well, we know that the signal has linear phase, and because the original digital sinc function goes negative right here, it turns out magnitudes cannot go negative, of course. That would be very hard. So what you have to have is a jump in the phase by pi. Essentially, during these intervals in frequency, we have to multiply by e to the j pi to make the mathematics work out. When it goes back positive again, we need to multiply again by another e to the j pi to make it go back to being a positive quantity, so we need another jump of pi. So in some sense, these jumps are all artifacts, but they're there to make the math work out. And when you compute spectra, you will see this, as you'll see in a second. But it's easy to see what they are. They're just a case where there's some, let's say, linear phase, and the thing that has the linear phase goes negative. All right, so what happens if we compute and plot, rather, the DFT? So here's the sampled version of that digital sinc function and its linear phase. And here's what happens when you plot it for the case where the transform length is exactly equal to the duration. And I don't know if you can see it very well, but there's a value at k equals 0, and all the other values, k equals 1, etc., all wind up being at the zeros of the digital sinc function. So our spectrum calculation wound up being that capital S of k was capital K, that's the value 10 up there, turns out to be capital K, delta of k, a unit sample at k, at frequency 0, k frequency index 0. Well, that doesn't look very right. How can this thing yield the original signal back? Does the inverse DFT formula work? Let's take a look. So here's the inverse DFT formula, and I'm going to go ahead and put in the formula for our spectrum, and we multiply by e to the j 2 pi in k over capital K. Well, the capital K's of course cancel, and the only thing we get because of the unit sample is just the first term when k equals 0. All the other values of the spectrum are 0, and so after we see everything, all we get is this. Evaluated at k equals 0, well, e to the j0 is 1 for all n. So we indeed get back our original signal, even though it doesn't have all the detail that we know is there from the DTFT. This is why you pad. So here is a more calculations of the spectrum of the same signal, but now I'm padding. So here I extended the transform length by a factor of 2. I added 10 zeros, tacked them onto the end of the original signal, and sure enough, what you get back when you plot it is you start sampling more often. If you go up to a much larger length, 64 in this case, you now see that the spectrum portrays all the detail of the DTFT, and you can see a lot of spectral detail. And emphasize, though, if all you wanted was to compute the spectrum and to get the original signal back, all you need to do is use the same transform length. That's what I showed mathematically. If you use this formula and look at the inverse DFT, you will also get the original signal back, but you'll know how the spectrum behaves, the DTFT behaves, in more detail, and a lot more detail here. And this is what we did when we computed the speech spectrogram. I used a longer transform length than the duration of the data in order to see the spectral detail, so I could see the formant structure and the pitch structure in the speech. I'm going to go over in a later video how we actually compute spectrograms and how this all works. But suffice it to say, padding is a very, very important idea if you're really interested in the spectrum and you want to see its detail. So, this is the DFT. This is not a new transform. It is a sampled version of the DTFT. And because of that, it shares similar properties. So the only thing we needed was to have a finite duration signal, and we sample the spectrum. In that way, we can compute the spectrum and get back the original signal. But we also know that you can pad with zeros, extend the signal with zeros, and take a longer transform, and that has the effect of sampling the spectrum more finely. And that is very, very useful in spectral analysis when you want to see all that detail that's there. Now, another little fact which comes up in practice, remember that positive frequency only goes from 0 to capital K over 2. If you look at the spectrum, which is what the DFT functions will do for higher values of K, they're just going to be a mirror image of what happened for the positive frequency side, from 0 to K over 2. So there's no real reason to plot it. You see what I did when I did the plots. I only plotted over that range. The other part I can find because of the conjugate symmetry properties. So this is the DFT. This is the workhorse in computing the spectrum of a signal in the digital signal processing world. Well, now we're going to next video, we're going to talk about very efficient ways of computing the DFT that really has very many applications in practice.